Here at the Naval Postgraduate School within the Space Systems Academic Group, we have been working on the latest high-altitude balloon launch under former astronaut Dr. James Newman. My name is Gavin. I worked on a team of 3 where I was responsible for the structure. My associate Yusuf built the electronic hardware, and our third counterpart Paul oversaw the payload. Our goal this summer was to test previously designed electronics with a new radio antenna, a separate payload, and software developed as part of a thesis to get better telemetry between the ground stations and ensure that the bus software does not permanently crash while in flight. Traditionally, space systems lab experiments are designed to physically fit within a CubeSat form factor, so we decided to go with a 2U standardized shape. We made use of the existing rail system, however all of the components inside are specialized. Each piece was designed to be easily 3D printable, adaptable to any future project, and as modular as possible. A unique component is the integrated ascent and descent piece that can be attached to any CubeSat size, enabling the balloon attachment line and primary chute to securely mount and be released via command. Another component is the electronic stack that can be installed, tested, and removed with ease even in final configuration.
This here is the bus hardware, which consists of the electronic power system, EPS, and command and data handling board, CNDH, which is the brains of the CubeSat. The EPS has the capability of taking battery and solar power, but for this test flight, only 8-volt lithium batteries are used. 8 volts enters the EPS and comes out in discrete mounts, specifically 5 volts, and powers the CNDH, which is then distributed to the N920 radio, Raspberry Pi 0W, and Bionics GPS. Aside from the radio, the electronics are the same as last flight, but this time the focus was to test its power consumption and new software. In the previous flight, the HAB software crashed, and there was no way to reboot, so as a precaution, the software now has a built-in rebooting system called the Watchdog.
Our payload consisted of a Tracker 2 data radio, 9-volt battery pack, and Bionics GPS receiver. Our launch this summer was the first Space Systems Academic Group high-altitude balloon launch in over several years to include a Tracker 2 data radio, which can relay messages and send data packets which include GPS and altitude statuses over the 2-meter amateur radio band. In the event of a nuclear detonation and an electromagnetic pulse that would knock out existing communication networks, small data radios could be deployed via high-altitude balloons, quickly setting up a mobile network. As a proof of concept, we set up a Tracker 2 radio to send packets with altitude, GPS location, temperature, and velocity over the Shared Automatic Packet Reporting System network, abbreviated as APRS, which is a shared network of digital repeaters that retransmit messages and link them to the internet, which allows us to track the payload on the site aprs.fi.
To predict how the weather may affect the flight, which determines where it will land, we used an online program called HAB because it allows us to use the balloon's mass, ascent and descent speeds, starting location, and time to predict the flight and landing point. A prediction is never guaranteed, so to test for problems, the time was adjusted 2 hours before and after the scheduled launch time to see where the balloon would land in a 4-hour period. Since the range of times resulted in the balloon landing in a similar area, the flight was a go for launch.
We drove out to Los Banos and launched near a canal, since it was an area free of power lines and traffic. Directly after the takeoff, everyone got into their vehicles, chased the balloon down, and maintained communication with each chase vehicle as we traversed through the valley. The route deviated slightly, and the bus ended up landing in Winton safely between some trees. The structure, however, did get damaged because of improper deployment of the parachutes that badly tangled the lines.
Ultimately, it was a good recovery, and the mission was deemed a success. The communication with the bus during flight was better than previous flights due to the new antenna on the CNDH, and all operating parts were recovered, allowing us to build another flight-ready bus. For analysis, we had a visualization of the data thanks to our fellow intern Divya and the tool she had created.
The data visualization aspect of the project involved using 3 coding languages, JavaScript, Python, and HTML, in addition to a Python framework called Dash. This was used to visually represent the real-time and post-processing data from the bus. The data was received from a log file for the post-processing data and directly from the HAB for the real-time data through a UDP client and server setup. The code I wrote split the data based on its command number and created CSV or comma-separated value files. From there, the code used the CSV files to generate graphs and data tables. The data being displayed in this manner allows for easier detection of anomalies, which is especially useful during testing, and can be used to review the data during and after the flight so that future improvements can be made.
For the future, we are planning for a longer flight, better antenna placement, and a real-time data visualizer. This concludes a brief overview of a successful summer interning at the Naval Postgraduate School's Space System Academic Group.